What's that? Oh god, yeah. We don't need that.
I think you might be muted.
Let me see. Okay, cool. Oh, my volume is so far down. I'm on the wrong microphone. Hold on a sec. Good audio. That's good. Crank that up. And crank this up. Oh, yeah. Alright, how's that? Testing 1, 2, 3.
Yeah, we can hear it.
Cool.
Or at least I can.
1 is the same as infinity compared to 0, so we're good. Alright, well, you made it. So this is our last class of CSE223 and the last class of the CS sequence here at Clark. So first of all, congratulations on making it through all of this. This is an intense sequence of computer science courses. It's not just the material, which is a lot of material, but it's the cumulative nature of it, the fact that so much builds on things that we do previously, and so by the time we get here, we're building on a number of concepts. So it's a significant accomplishment getting through this whole sequence. So nice work, everybody, on that. Let's see. So SLPs happened on Tuesday, and that was a really nice job. So most people showed up for that. Izad and I took turns being in the main room and running around and listening to talks. And so I got to listen to a few talks this time. And the ones I listened to were really good, very interesting stuff. And I think the people who were visiting enjoyed going in and listening to student presentations. So any sort of general reflections or thoughts or comments on the SLP presentations Tuesday, or the whole SLP project across multiple quarters? Any feedback?
You can always keep it going. That's my plan. I kind of failed on some big parts of mine, but I have a new strategy to come back and fix them in some way.
Cool. Yeah, these kinds of projects are usually not, work on it this much and you're done, right? Ideally, the project is something that people are actually interested in working on, not just to, get their 10 points on their grade, but it's something you want to be spending time on. And you've heard me say before, I think, that, when I was an undergrad, very little of my learning happened in the classroom. I went to class, I learned how to, read the professors, anticipate what they would ask on exams, and I got good grades. But most of my learning happened in, my own time hanging out with friends working on projects. And I still believe that's, the most important component of learning is the programming and, design and problem solving that you're doing on your own. And the most likely scenario for you to spend, a serious amount of time and energy on that is if it's in an area that you're interested in, right? A problem that you're really trying to grapple with. So you really want to make a video game where you're going to spend a lot of time, playing around with code and trying things and debugging and so on and so forth. Most people are not, waking up in the morning saying, oh, I really want to make a linked list today, right? I might, but most people aren't. And so you make your linked list code because it's due, in 3 days or whatever. So I really hope the SLPs are things that, people were able to kind of sink their teeth into and get some degree of satisfaction out of. And definitely if it's not something that you feel got to the place you wanted it to, I hope people will continue developing their ideas. And occasionally I've had students who, take their SLP and end up commercializing it. and that's pretty cool to see.
You know, it's funny, Azad actually came in and saw my presentation and offered some wisdom, which was pretty good.
Oh, cool.
And because I was telling him that, you know, when I was making a game, it was the first level that took forever, and then 2 and 3 were pretty quick because I've already learned everything. And he said, yeah, most of the time, if you have the time and money as a developer, a lot of the time they'll make their first game, throw it away, just so that the second game is flawless and better.
Nice.
You know? And I was like, wow, that's pretty insightful, you know?
I think there's a lot of truth in that, yeah. And I've yeah, go ahead.
I got a lot of inspiration from PA5 in this class to how I want to change my SLP's network architecture in the future. So
Oh, cool.
I'm glad I still want to do it after this because now I have some more tools to go ahead and fix it.
That's awesome. Yeah, bonus.
One of the other guys in my room had brought up a good point, and it kind of sucks being on the presentation side of the SLP because you don't get to see what everybody else worked on. You only get a couple people.
Yeah, that's a bummer. And that's one of the downsides to doing this remotely in Zoom. When we do this in person, it's a totally different experience. Because first of all, there's a lot of manual labor because you have to open the doors, the sliding doors on one of the classrooms to make space, and then everybody starts pulling tables out of the main rooms and bringing them into the hallway and the digital lounge, and you get a good workout with all of that. And then you've got, you know, this whole side of the STEM building just filled with students talking and showing their projects and so on. And usually, you know, people work in groups on these, and so after things get going, people will take turns. One person will stay at their table to talk to visitors, and the other one will go around and just visit other students' presentations. And so you can get a really good handle on what other people are doing, and that's pretty fun. And for me, I can spend the whole time walking around, just, you know, visiting student presentations, listening to what they did, asking questions, things like that, and that's really fun. And I don't get to do that with the virtual setup because, you know, we stay in the room to direct visitors into rooms and so on. So there are some advantages to the in-person version of this, which I don't know if we'll be going back to that or not. But yeah, it would be nice if students could see what other students are doing. But, you know, there's that announcement I posted where if you want, you know, unlimited fame and fortune and immortality, you have the option of sharing a short video of your presentation. And the main reason we're asking people to do this is just to have, you know, kind of an archive of projects students have worked on, mainly for new students, so that when students come in September and I say, you know, SLP, and they say, well, what should I do for an SLP? I can say, hey, here's, you know, videos of what past students have done, get an idea from there. Again, when we're in person, there's a big hallway right outside the Nerd Cave in the STEM building where the final posters that people print for their presentation, those are hung up in the hallway. And so you can just walk down that and see, you know, 40 or 50 past projects and get ideas like that. So if you want, you know, fame, fortune, possibility of a Hollywood contract if someone sees it, you can upload a short video presentation of your SLP. And I sent an announcement yesterday, I believe, with details of how to do that. Purely voluntary, but, you know, potentially helpful to future students and another chance to talk about your stuff. Yeah, it is kind of interesting to be on the other side of that, right? Where you're going to be like the old students that new students will be looking at in fall. That's kind of cool. Any other thoughts, comments, ideas, suggestions? Let me put something out there that I asked yesterday's section. At one time, I used to, for SLPs, give students a list of projects that they could choose from. with the understanding that if they wanted to do something different, that wasn't on the list, they could, talk to me about it, and if I approved it, they could work on that. But basically having a set of projects to choose from. What do you feel about that? I mean, would that have been helpful to at least have the option? Would it have been a distraction? Any feelings around that?
If it was like super loose, so like a video game, which is really broad, you could take it a number of ways. It's just like, here's a couple of things you could go ahead and work on, but it's really, really broad.
Right.
I don't know. I'm not a very creative person. I don't think on my feet too well, and I think that kind of helped me step out of that and come up with my own idea.
Oh, interesting.
By not having a list.
Okay.
Kind of nurtured that side that I don't really get usually.
Right.
I would make it like a suggestions list, really. Maybe nothing that's truly required, but a lot of really good suggestions.
Right.
Yeah, I think you had talked about that. Like, you didn't give us a printout or anything, but it was kind of like, you can make a game or you can do this. Like, I think that was helpful, but I don't think any more than that would have helped or hurt me. I don't think. Okay.
Yeah, and I know some people come into this and they don't really have ideas. They haven't been trying to find time to work on their dream project, for the past year or something. And so offering ideas, I think, can help in that case. But I do like students to be able to say, like, hey, there's this thing I really want to do. Can I do that? And that's always cool. All right. Well, again, nice job on the SLPs. And grades are posted on that, and basically everybody who showed up got 50 out of 50 because no complaints about the presentations. They were all really good. So that's done, and I think you are done with all aspects of this course except for the final exam. So that's kind of our main topic today is just sort of talking about the final, going over logistics, maybe talking about some topics. And so on and so forth. The other thing I thought I could do today, if it's interesting to people, was go through some solution code for PA5 and PA4, which we never went through, just to kind of show you how I approached it, which was a solution I came up with a few years ago. It's actually not how I would do it today, but it's a solution. And PA5 seemed good by and large. Except a number of people did not turn it in, and some people who turned it in got the first half of it working. So the GUI set up, the initial connection, sometimes a swapping of the names, but then weren't able to get the mouse clicks to swap.
It was pretty tricky to write the synchronization functions, in my opinion.
Yeah.
Something I really want to go back and refactor for fun.
Yeah. Like I say, if I were to rewrite this right now, I would probably do it differently because this was the way I first wrote it, and then that was before I had even first tried describing it to a class. I think this was 2 years ago, the last time I gave this. And so it is nice after you finish something to be able to go back and look at it and see, is this does this make sense, or would it make more sense to create another class or to move these things from one class to another, and so on. And that's a useful exercise because the goal is, that over time, as you create larger projects, you're better at, coming up with that sort of ideal layout and organization up front. And I think you can get that by, doing what you do and then going back and looking at it and maybe refactoring it and so on.
I think I would try to make it server authoritative too. So some nebulous computer could host the server and two clients could connect over the internet that way.
Ah, yes.
That was my whole SLP, but I failed to get it working. And
Oh, okay.
That's why I want to go back.
Yeah. Yeah,
That'd be
so
kind of cool. Just put in like who you're trying to connect with, like a name, and if that name is there, then they can just connect together, whatever.
that would be cool, like a game server, right?
Yeah.
And that's sort of the more classic client server model is if you're really just connecting to this thing and it's dedicated to you and it doesn't accept other connections, it's not quite, it is a client server model, but it's not what we usually see. For example, when you want to connect to the Linux machine, you say SSH and you put in the Linux name. You're talking to a server program called SSHD, and it asks you for your password and so on and so forth, starts a bash shell and such, but the server that you connected to is not doing all of that. It really early creates a new process to do all of that communication with you, eventually change into a bash shell and so on and so forth. And the server that you originally connected to is still sitting there just waiting for more connections. And so it's doing kind of what you're describing for a different version of NetDot, where you would, get a request to play the game, and they would either create a new process to do it or put you together with another client who had connected, and then the two clients would play each other.
Well, technically, if you did it that way, you can set it up to where it accepts different IPs, right? So you don't have to be on the same local network.
True.
So
That'd be kind of cool.
the reason I was always so fascinated with it is because of you could do server-side anti-cheat. This isn't really like a game where the state of the game changes so much that it would matter. But like, let's say you're playing a game and somebody's trying to move 1,000,000 miles an hour.
Yeah.
The server could see that vector and say that's a problem.
Right.
Somebody's cheating, right?
Yeah.
But it also makes it like super easy for any of your friends to just go and play the game and put in some URL to go join the server.
Right. Yeah, that would be a fun, if this was a longer class, or if there was, a sequel to this class, that would be a fun direction to take this. Because then, you could just, put up a website and, list of people playing and their level or ranking, and you could choose someone to play, or it could put you with an appropriately ranked player and so on.
You can play around with databases also.
Yeah.
Like a true full stack.
That's a curious question. So, obviously, this is kind of the last of the series, so we'll be going off to university. But at what point, do you do web development and stuff like that in university, or do you just expand on C and Java and some of those languages?
So there's a smattering of courses that you can take. I don't remember the names of some of them. So you'll take a system programming course your first semester, and that's mostly C, and it's low level, and it's nitty gritty, and it's bit manipulations, and it's an intense course. So that's like 222, but a much darker version of it. But it's an awesome course, great subjects. But you can also do like a game design elective. You can take a networking course, computer security courses, cryptography courses. And there's something related to web development, not so much creating web pages, but like making a database, back end stuff, playing with Flask and things like that.
Okay, so it kind of depends on what path you decide to go down.
Yeah, and I think there's a lot of electives. So there's some core courses you have to take, and then there's technical electives. And you can kind of pick and choose embedded systems or game design or stuff like that.
Yeah, that cybersecurity sounds pretty cool.
Yeah. And a lot of this stuff changes all the time because a lot of these fields are up and coming. Kind of like machine learning is a field that's probably different every year. So I would guess.
UW, they have some courses in AI and things like that. Robotics. That'd be kind of interesting.
Yeah, there's tons of opportunity out there, and Clark is really kind of like intended to make sure you have the basic tools you need to be able to do these more advanced courses. And then the more advanced courses are the ones that are, maybe more topical to what you might do as a career, or, if you were going on to graduate school, things that would, turn into research areas and so on and so forth. And I hope that everybody's going to have a really good time at university. It's usually a lot of fun. It's definitely usually a lot of hard work, but very satisfying because you're doing sometimes cutting edge stuff. You'll also have a capstone project, which is similar in idea to the SLP, but will probably feel a lot more intense, a little more micromanaged. Sometimes there's things like, weekly meetings with progress updates, and you have a industry sponsor that you're working with that you're basically doing the project for, and there's, periodic presentations to the sponsor and so on and so forth. And that's all really good experience, but with its own set of challenges. So I'm excited for people. I loved being an undergrad. It was like, the best time as far as learning. And I think it's going to be good for people here. All right. Well, let's go on to talking about the final exam. I want to make sure we have time to get through that. And I talked a little about my PA5 solution yesterday, so you can always watch that from the video. But let's talk about the final, and let's begin with logistics. So final exam is Thursday, 1 o'clock to 2:50. Which is weird because graduation is like, a few hours after that. So this is, same day. So I won't get it graded before you graduate, but, that's okay. Anybody here going to commencement? Maybe.
Take her dinner. I just sent a text.
No, I don't have. I didn't do the physics, the second part of the physics.
Oh, okay.
I'm going to BW and it's not required, so I don't get the AA. So I'm gonna.
Okay.
Just move on.
Yeah.
Physics attempt was a disaster, so.
Okay. So if you're transferring without finishing all of the requirements for the AST, don't forget that after you complete those requirements, you can send those credits back to Clark. And if you do that, in 2023, for example, you could go to commencement at the end of that year, if you want to do that thing. I think commencement is really fun. I went to one of mine throughout school. I've got, multiple degrees. I only went to my undergrad. I wish I had gone to the others. Because it really is a nice kind of seal on what you've done. And it's a nice sort of, concluding moment of what's a very long and trying process. I'm not going to make it to commencement this year, unfortunately, but hopefully some people can go.
I would have loved to meet everybody though, because
yeah, me too.
I've done this whole.
And I feel like we've all been together for so long.
Yeah, totally. And at the end, they have all the faculty line up outside, and the students, when they leave the auditorium, they walk through this gauntlet of faculty members, and that's really fun to high five people as they go by and so on. Except I have no idea what most students look like, so that would be interesting because we'd be walking right by each other. But
It really does kind of suck because I've had you for 4 semesters straight.
yeah.
for like every computer class you taught.
Mhm.
But I've never seen your face.
Yeah.
At least in person.
Yeah, I'm here, but yeah. So these are strange times. But anyway, all right. So final exam. So Thursday, 1 o'clock to 2:50. So the regular class time. But it's on Thursday, not Tuesday. That's the way that the schedule is set up. There's obviously no class Tuesday. Today's the last class, and then the exam will be a week from today. And as far as logistics, it's going to be basically the same as the midterm was. So I'll upload an exam to Canvas sometime next week, and this will get locked, and then it'll unlock automatically at 1 o'clock. And all that this is telling you is basically, you know, it's the final exam. You're going to upload your solutions as a PDF file. Make sure you submit by the deadline, closed book, etc. But you're allowed the same 6 double-sided pages, 12 single-sided of notes, any format that you like. So if you can't remember, you know, how you define a generic when you say like linked list or hash map, just throw a line of code, you know, on your notes to refresh your memory. You can put anything in there that you want. So this will run 1 o'clock to 2:50. It will not shut down automatically though. So if you have an extended time allowance, just keep working, and don't worry when you submit it that Canvas says this is late. I'll add on your time allowance and count it as on time. If you had difficulties on the midterm with the mechanics of, you know, writing your answers, scanning them, putting them into a PDF and uploading, come by office hours. We only have office hours tomorrow morning left, but you know, come by office hours and let's figure out your setup and make sure it's as streamlined as possible. And there's lots of things you can do to save time, right? If your scanner always saves your files into the same directory, just open a folder with that directory. And if it's got a bunch of files in there, move those out of the way, put them into like an old folder or something, so that when you scan, you know, a file pops up, you can just drag it into your document. Keep a document open before the exam starts, so you can drag your files into there. Make sure that, you know, your defaults are set up, know your hotkeys, so you can like Control S to save instead of doing, you know, file, save, etc. Little things like that can move this upload process from being a time suck to being just kind of, you know, like breathing or something. It's just something you do in the background, so that you can maximize your time. And you want to definitely figure that out ahead of time. Don't try something new on Thursday that, you know, breaks or needs an update installed or crashes your machine or something. I'm sensitive to this right now because my machine has been acting up for a few months and a lot more for the past week, and really badly for the past about 36 hours. And so I just upgraded my Linux to 20.04, and it's like a new machine. My Bluetooth started working again, my audio started working again, and all this other stuff. Oh, fun. Yeah, that's always a factor. All right, and as far as what you can expect on the finals, so there'll be obviously some coding questions, and as usual, there may be questions where I ask you to write some code, which could be, you know, an entire class description, or it could be an entire program, a class with a main method, or it could be, you know, a few lines of code. I might give you code and ask you questions about it, or ask you to make changes to it, or add things to it, or fix something in it, and so on. So it could be writing some code, could be analyzing some code, and there will probably be some short answer, multiple choice, fill in the blank, true, false, matching, those kinds of questions on some of the conceptual stuff. Write a poem about hash tables or something like that. No, I won't do that. So topic-wise, this is just kind of, this is not all-inclusive. This is not based on the actual exam, because the exam hasn't been written yet. But this is just kind of a hit list of things that we've gone through that I think are some of the major points. And if there's anything you want to talk about as far as reviewing topics, definitely say that, rather than just, you know, wait for me to get to it going through this list, because this is a long list and it's kind of generic. So if you're, you know, wanting to know about the paint method or the toString method or what a hash map is or something, ask those questions and we can go through those first. Or as we're going through these, if questions come up, definitely go ahead and ask. Otherwise, I'll just ramble on for the next, hour or so. All right, commencing with the rambling. So, writing code, analyzing code, answering questions about code. We talked about that one already. So that's the majority of the exam, probably more than half the points, coding questions. Java, the notion that Java is an object-oriented language and what that means, right? Objects being, things that contain not just, different pieces of data, but also code that interacts with that data. And so this idea of encapsulating code and data into an object, right? So we make a class that says, here's an integer, here's a bunch of strings, here's an array, here's a linked list, all this stuff, and here's the code that, interacts with it. That all gets bundled into this one thing, and this is an object. And it's got all that stuff inside it. So that's one of the ideas of object-oriented design. It's a thing we call encapsulation. Java is an interpreted language, so when you compile it with the Java C command, you don't get Intel machine code, right? You get something called bytecode. And bytecode is, binary code, it's machine code, but it's not machine code that an Intel processor understands. It's not machine code that an ARM understands. It's not machine code that a PIC processor understands. It's machine code that's understood by a different machine called the JVM, the Java Virtual Machine. And it's an emulated CPU. It's a program, probably written in Java, that acts as if it was a CPU. So it fetches an instruction and decides what to do, and fetches another instruction, decides what to do, and so on. So it's a compiled language, but it compiles down into this machine code that has to be interpreted, executed one line at a time by another piece of program, another piece of code called the JVM. So it's compiled and interpreted. And the fact that, it doesn't compile down to Intel code or ARM code or PIC code, but it compiles down to this code for this virtual machine makes it really portable. Because as long as you have an implementation of this virtual machine on whatever your platform is, your platform can run Java. So if you put a JVM on your smartphone can run Java. That's how Android works. So very portable, slightly slower execution because it's not running directly on the hardware, but all these benefits because of that. So object-oriented, right? Bundling of code and data. So that's encapsulation, and then information hiding is the other mainstay of object-oriented programming. And information hiding is basically, we take some aspects of the things in an object and we tuck them away. We put them behind a firewall. And we say, you don't get to interact with those. You get to interact with these things up here, this interface that we're defining. And so this gives us a software equivalent of an abstract data type. So we can create a rectangle class, and we can say, okay, here's how you construct a rectangle, here's how you find its area, here's how you find its perimeter, here's how you change its dimensions. And the user has no way of knowing how we're implementing that class. Are we storing, the width and the height, or are we storing the width and the length of the diagonal? Are we calculating the area by multiplying height and width, or do we calculate it ahead of time and just return a value? Right? Those details are hidden from the user, and the user's interface with our data structure is just through these public methods that we create. And so we can do things inside our class that if the user interfered with might break our code. So for example, we might have a sentinel node on a linked list. User doesn't know that. They say, make a linked list, add something, search for something, delete for something. And whether we have a sentinel or a doubly linked list or a circular list, they don't know that, right? So information hiding and encapsulation, those are the things that we see for object-oriented programming. All right, general Java syntax. You should know all of this. You've been writing Java code for at least 10 weeks now. You should be pretty comfortable with basic statement structure, ifs, loops, variable declarations, starting a class, defining a main method, all that kind of stuff. If you're unsure about that, definitely go back and spend a little time writing some code without using any resources, right? Without using notes, without looking at the text, without starting with an old piece of code. Just go into the editor and try to write a Java program that prints hello world. And yeah, you have 12 pages of notes available on the exam, but if you feel very comfortable sitting down with an empty window and typing in code that you can compile and run and print hello world, you're going to be more comfortable during the exam, right? Instead of constantly flipping through your notes and trying to copy exactly and make sure you get the brackets in the right place on the argument list and so on. So spend some time just writing code, and along those lines, right, spend some time going back through your old programming assignments, and maybe redo some of those. Particularly the older ones, because those are further back in our memory probably. Maybe try redoing those and do them from scratch. Or at least think about them and think about how you would start them. Imagine that they were an exam question. Would you be able to make a stab at writing code to do whatever that assignment did? So old code is useful. There were a few ODPs; those can be useful too. The textbook has 40-some chapters on Java, and lots of sample code inside there, and so lots of ways you can practice with that. But make sure you're comfortable with general syntax, and you're not getting tripped up on details like semicolons and curly brackets and stuff like that. All right, constructing a class. So the class keyword, creating methods, creating constructors. These are sort of the main things we write. And then constructing a class. So using the constructor to create an instance of a class. So the new keyword. And then accessing variables and methods inside a class. So object name dot field or object name dot method parentheses list of arguments, and if it returns something other than void, something equals object dot method, etc. Again, you just want to make sure you're very comfortable with those, just so that they don't start playing with you when you're taking a timed exam, and maybe worried about other exams you have to take and so on. The more practice you've had writing this kind of stuff under test conditions, the easier it's going to be. So creating an instance of a class, accessing variables, methods, signatures. So signatures are just the method name and the types of arguments. So you can have a method named blah that takes an int. You can have a method named blah that takes 2 ints, and a method named blah that takes a string. Those are separate methods. They have different signatures. And when you call a method, it uses the name and the types of arguments to figure out what method you actually want to call. That's all there is to a signature. Static methods or fields. So static methods are sometimes called class methods, and they're accessed by using the name of the class itself. You don't have a particular object of that type of class to run the method on. You just use the method directly from the class. Non-static or instance methods you run using a particular object of that type, a particular instance of the class. And the difference being that, for example, the area method for a rectangle, right, you need a rectangle to say what's the area of a rectangle. It makes no sense to just say, let's call the area method and see what I get back, unless you have a rectangle in mind. So area would be, you know, an instance method, a non-static method. But maybe you want to know what's the length of a diagonal for a rectangle with a given height and width. Maybe that's some useful piece of information. And you could construct a rectangle of that height and width and then ask for its diagonal length. But maybe you don't really want a 5 by 7 rectangle. You just want to know, if I had a 5 by 7 rectangle, how long would the diagonal be? So you might make the diagonal method static. And you could say, you know, uppercase R rectangle dot diagonal parentheses 5 comma 7. And it'll tell you what the length of the diagonal is. And then different versions of constructors. Constructors have a signature too. The name of the constructor is the same as the name of the class, but the argument list can have different types of arguments. So you can have multiple constructors, and we did this with, you know, making a rectangle with 1 argument or 2 arguments, and so on and so forth. All right, and then there's data structures. So we've worked with a bunch of data structures. So arrays are the first thing. And we'll talk more about those in a minute, but you know, arrays are a simple type of data structure from C as well. But linked lists, and there's a linked list class, but we can also make linked lists ourselves. We worked with trees, so we made a decision tree. We played with binary search trees in class. There's hash maps, there's stacks, there's queues. We could implement heaps. There's all kinds of data structures. And the stuff we did in 222, we can do that in Java. Or, you know, for a lot of these classes are predefined. There's a class called hash map we can use to play around with hash tables. Recursion should still be, you know, near and dear to you. And we haven't written a whole lot of recursive code this quarter, but you know, if we implemented a binary search tree, we could write a recursive height function, and that wouldn't be too startling. So generics are the idea of you know, if you make a hash table, which the class is called hash map. Well, hash table, you know, we have some kind of key and some kind of data value that we associate with the key. And the key goes through some sort of hash function to tell us where the value is stored, and there's collision handling and all this stuff. And we don't care about any of that. If we're going to use a hash map, we just want to say, hey, I want a hash map called, you know, index. And maybe I just want to construct without any arguments. And so hash map is an example of a class that takes generic parameters. So what type of key and what type of data we have doesn't change the code fundamentally. So with hash map, when you declare something to be an object of this type, you specify what type of thing the key is and what type of thing the value is. And you do that by putting them in angle brackets. And then when you construct, you also have to specify the type of the key and the type of the value.
I was going to ask a question about this.
Mm-hmm.
So, would you just consider a dictionary as a hash map that only takes strings as indices?
Are you talking about like a Java dictionary or just a plain old dictionary?
Probably both.
So yeah, if I wanted to write, you know, a dictionary, some code to create a dictionary for, you know, predictive typing or something like that, yeah, that would probably be a hash map of strings. I'd use a string as the key, and then the value would probably be, you know, some kind of object that includes, I don't know, maybe a definition and a frequency account and common misspellings and whatever else. And then, yeah, go ahead.
You could probably just make a class definition, dictionary extends hash map with the key being a string and b being an object, and just call it a day.
You could extend it, or you could if you did that, when you constructed, you'd still have to. I don't know if you can extend a generic and in that extension hardwire those parameters. That's an interesting question. But I mean, you could certainly wrap a particular type of hash map inside another class that would just declare this in the beginning of the class as a property of that object. So that's generics, right? So it's just a nod to code reuse, so that you don't have to write 15 different hash map classes. You have one set of code, and you just specify what types of parameters you want. And when you write the actual class, if you're implementing the hash map class, you can use these in the definition of it. So you can say class hash map angle bracket, and then you can use these parameters in place of a particular data type. And so it's almost like a macro in C, where you do a pound define. You can call these whatever you want, and then you can use those in your code, and they get replaced with what was used here when the person using the class specified a declaration or a construction.
It's really funny you mention that. I was talking to a friend yesterday who got inspired to write his own game of dots, but using Rust.
Oh, cool.
For my code, and he showed me that in Rust, the way generics work, you kind of use macros to use them. What you can do with them is you can make them be like bar args.
Oh, cool.
So with vectors, which is just a list in Rust, you can actually make it multi-dimensional with the generics.
Oh, cool.
So like a 3-dimensional vector.
Nice.
Yeah, it's really cool.
Yeah, you gotta love playing around with different languages. There's so many languages out there, and different people respond to different languages differently. Haskell is a language. It's functional, and some people go really crazy over it, and it's just kind of fun to play with. Something like very different from C, for example, which is the style of most programming I've done. It's fun to mess around with different pathways in your brain.
Rust has really made me consider this class a lot, and how we've been building things in a more object-oriented manner, where there's kind of this shared state where as long as you have a reference to an object, you can invoke public methods on it from anywhere, right?
Right.
Well, in Rust, you can't necessarily do that, because you're only allowed to have one writable reference of any piece of memory and an infinite number of readable copies. But the thing that makes that really hard is that any function or method on a class in that language, if it changes the state of the object, you still can't invoke it.
Oh, wow.
Unless you're writable.
Interesting.
So it's really hard to think of it in an object-oriented sense when you have that kind of ability to influence state.
Right.
Classes.
Cool stuff. And if you want to go the other direction, I mean, there are languages that are so far removed from object-oriented, and so one of my first languages I learned was APL, and APL is short for a programming language. It was created as a way to teach programming, and it wasn't meant to be an actual language that people would use. And the person who came up with it, somebody asked, "What's this language called?" And he kind of shrugged and said, "It's just a programming language." And so people started calling it a programming language, and then they started calling it APL. And it's very much procedural, but it's vector based. Everything you do is potentially done on arrays, possibly multi-dimensional arrays. And it also uses Greek characters. So all your letters are uppercase, and if you shift a letter, you get a Greek symbol. And so, alphas and rhos and thetas and things like that come into your program. And it's a fun language to work in. It's a very, very different mindset, though, to think about, doing something not by iterating, but by operating on an array of things. It's a language I've been predicting a comeback of for some time now. And I think maybe when we start getting serious about like quantum computer programming, people will start thinking in kind of a mindset of APL, because it's useful to be able to analyze a lot of different data at the same time, and that's a little bit where quantum computing starts to come in. Ruby is the bane. Go ahead.
Go ahead. You should look at Julia. That's kind of what you're describing.
Oh, really?
It's a newer language.
Okay. Someone said Ruby is the bane of my existence for no real reason.
It's funny to see how object-oriented is just so different in every language, too.
Right.
It's like you almost can't even really quantify it as a paradigm because it's so different. Like in Lua, objects are actually dictionaries, and that's the data type you can use, and you can kind of fudge a dictionary into its own class. And, with JavaScript, every class is a prototype, so instantiation is kind of inheritance at the same time.
Oh wow, okay. Yeah, no, I think there's a lot of truth in that, and I started playing around with Visual Basic eons ago, and that's object oriented, but I had no idea people didn't use those words. But it seemed cool, that you could like have this thing and get to these functions from the thing itself. And I started playing around with Arduinos, and Arduino is C++, basically. But I had previously tried to learn C++, and just kind of like ran away throwing up, because it didn't suit my style. I think it was the C out and C in thing that threw me. But then Java, started writing Java, basically writing C in Java, and it's like, well, this is really annoying, because they have all these statics and everything like that. But then somewhere it clicked, and like the stuff I had done decades before in Visual Basic started feeling like it was coming into play with Java, and then all of a sudden there's just this like transition moment, and it's like objects, But yeah, it's definitely different from language to language. And I think the common themes are fewer than people would like you to think.
Yeah.
All right. Well, anyway, generic. So iterators. So iterators are this idea of, here's a collection of data, and there's some data scattered around, and if this stuff is ordered, if it's an array, we can say, give me element 0, 1, 2, 3, 4. If it's in a list, we can say, give me the first node, the second node, the third node, the fourth node. If it's just in a pile of data, which is kind of what a hash map is, there's no way to say, okay, give me the first thing, give me the second thing, and so on. If we don't know what the set of keys are, we can't ask for the data one at a time. And so this notion of an iterator is a mechanism to say, hey, give me a first piece of data from here, give me a second piece, give me a third piece, so that by iterating through, we can access all the information in this data structure in no particular order, but be guaranteed that we've seen each piece of data exactly once. And the structure of an iterator is similar to what we've done with scanners. It's usually something like a has-next method, which tells us, is there another piece of data we haven't seen yet? And if there is, we can say next, and that will give us that piece of data. And in some sense, this is what happens when we read from standard in, for example. We don't know how many lines we're going to read. So we can't just make a loop and say, for I equals 0 to 10, read line number I. So we use this has next or has next line paired with next or next line. And that's the structure of an iterator. So things like hash maps, we can create an iterator construct an iterator from the hash map, and then use these methods to access data from there one item at a time. We didn't write any of those. I mean, maybe we did in class, but we didn't use that in any assignments. So I'm not going to, you know, expect you to know how to do that. But the concept of an iterator, the concept of going through a hash map like that, is fair game. How are we doing here on time? We got about an hour left. We got strings, arrays, scanners, and then the new stuff. Let's do a 5-minute break. And let's come back and finish this up. So we'll come back at just under 5 minutes. All right, so I'll see you in a few. All right, so let's see. Let's continue. So strings, you should know all the basic things that we do with strings. So finding the length of the string with the length method, using equals to compare two strings and see if they have the same characters, which is different from using a double equal sign. Compare to if we wanted to sort, see which one comes first. Character at to index a particular element because strings are not arrays. So if we want the third character, we can say character at parentheses 2. And the toString method in general, which we can use to take an object and return a string representation of it. And remember, toString does not usually print anything. It simply converts the object into some sort of string representation. And then, double equal versus equals. Double equal tells you, are these two objects exactly the same? Dot equals says, are the characters of these two objects, which might be different objects, are the characters the same? And that's usually what we're trying to do. All right, arrays. Arrays are a little funny. Not funny, haha. In Java, so integer bracket bracket x. Right? This declares x to be an array of integers, but x itself is null. If we try to say x bracket 0, we're going to get an exception. So before we can use this, we need to say something like x equals new int bracket 10. And that actually gives us an array of 10 integers. But with objects, with primitives, this is all we need to make an array, and we can do this in one line. But with objects, if we have, for example, rectangle bracket bracket rx, for an array of rectangles, and we say rx equals new rectangle bracket 10, well, now we can say rx bracket 0125 and get a rectangle, but the rectangle itself is going to be null. And so if we want to use, rx bracket 0, we need to construct that by saying this is a new rectangle and pass the dimensions of it, for example. So with arrays of objects, we have this sort of double construction we have to do. So we have to construct the array and then actually construct the objects in the array. So that's what this is referring to. And arrays come with a length field, and so up here if we say x.length, that would tell us how many things are in this array. Down here if we say rx.length, that would tell us how many things are in that array. And it's not a method, it's not length paren like it is for a string. It's just a field. When we create the array, this field is initialized to how big the array is, how many objects are in the array. All right, scanners and print writers. So this is the way that we've been doing input and output. It's not the totality of how we can do input and output. In fact, it's just one particular input and one particular output mechanism. Not the best, not the fastest, not the most convenient, but it's one way, and I wanted to not get bogged down with that in this course. So pretty much all the input we've done is through a scanner, and all the output we've done is either through a print writer or through system.out, which looks like a print writer. So we can read from standard in by constructing a scanner on system.in, and we can write to standard out by saying things like system.out.println. But more generally, we can make a scanner on a file, for example. So we could construct a scanner with an argument of new file, and we could put a path in there, and that will open a scanner that can read from the file. Or if we have a socket, we can construct a scanner with an argument of the name of the socket dot get input stream, and that would give us a scanner that can read from a socket. And then whatever we've done, once we have a scanner, we can use things like has next line and next line to read one line at a time, has next and next to read one word or token at a time, has next int and next int to read one integer at a time, and so on. And for print writers, we can construct a print writer with an argument that's a file name, or, you know, we could make a new file constructed with that file name, and that will give us a print writer we can use to write into a file. And so we can say, you know, the name of the print writer object dot print line, and whatever argument we put in there will get written to the file, followed by a new line, or just print if we don't want a new line. And the one tricky spot here is with print writers, sometimes we have to use flush. If we are not printing, if we're printing to standard out and we end our line with a new line, it will appear on standard out. If we write to a file or a socket, even if there's a new line at the end, it may not actually get sent to standard out until we call to the destination until we call flush, because most of this I/O is buffered, so it gets saved up and then transferred in bulk. Alright, class extensions. So there's the extends keyword, and we can say something like, you know, class let me stick to our convention. Class new class extends old class. All right, so it's defining a class with this name, but it's saying, hey, I want all the stuff that's inside old class to be part of new class. So all the methods, all the fields inside here are now automatically a part of new class. But with the twist that if I want, I can change some of those methods by rewriting them, or I can add new methods or new fields by just defining them. So I might, you know, do this and then have 3 methods defined in here. If those are not methods found in old class, they're additional. If one of those methods is also contained in old class, it overwrites the version that was in old class. So it gives you a starting point that you can build on and modify. And if when doing that, I've written my own version of some method in here, but I want to access the original method, that's where you can use the super keyword. And so super is a reference to what we call the base class, the class that you extended. And the main place we've done this is with Swing when we were doing painting. So we would create, for example, something called a My Panel, which extends a J panel. So it's got all the stuff a J panel has. The ability to set the size and add listeners and all of this other stuff, right? And maybe the only thing we do in here is we make a public void paint, which takes a graphics argument of type G. Well, there's already a paint method in here, so we're overriding that paint method. But we don't want to have to write the code in here to say, let's draw the border, let's, you know, fill in the background, let's draw the widgets that are on here, and so on. And so typically the first thing we do in our paint method is we say super.paint G, and that will call the paint method from this class. So that's the main thing we've done with super. This is one of the spots where a factory might help. Agreed, yeah. Alright, so super keyword, defining a constructor, exceptions and exception handling. So try, catch, otherwise blocks. We didn't play a lot with otherwise. But basically, you know, you can put one or more statements in a try block and then have a match and catch block. And if an exception occurs in the try block and that exception is listed as an argument in the catch block, your program jumps into the catch block and starts executing that code. And if you have an otherwise block, that block is always run whether you succeeded with the try statements or you ended up in the catch statements. At the end of whichever block you finish up with, you'll always execute what's in the otherwise block. And the main thing to know here is that sometimes you cannot know if an exception is going to occur. If you're trying to make a connection to a server socket on some remote machine, you don't know if that's going to succeed or not. You don't know if the host name is going to resolve. You don't know if that port number is going to be available. So really, if you don't want to throw an exception, your only option is put this inside a try block. And the compiler forces you to do that. But, if somebody wants to calculate the square root of something, and you're worried that they might ask you to take the square root of a negative number, don't throw it in a try-catch block. I don't think that actually throws an exception. But don't use a try block if there's something that you can easily check for. If you're asked to access, element n from an array, check to see if n is bigger than or equal to array.length. Don't just try to access the nth element and do it in a try block and catch the exception, right? It's expensive to throw an exception. It's a break in the execution stream, so it will drastically slow down your program. And it's harder to debug. If this is a normal thing, like let's say you wanted to print all the elements in an array, you could put it inside a for loop, right, or a while loop, and just keep incrementing the index and put that in a try block, and when you get an exception, you're done, right? That is not the way to make friends. Because these are called exceptions because they're exceptional, they're unusual. And somebody looking at your code would not expect the except block to fire unless something goes wrong. So use these sparingly. Feel free to use them, but use them sparingly, and put them around the smallest set of code that it makes sense to check for an exception. So that's the main details with using try-catch. All right, swing, GUIs, graphical interfaces. Overriding the paint method, we just talked about that a minute ago. Basically, swing is this big package of all these different classes. You're not expected to memorize the details of that. I don't expect you to be able to write code to, construct a JPanel and add a button to it and set its text field to this and add a mouse listener. We have things like Window Builder or other IDEs to do that for us. That stuff is so boilerplate. It's so repeatedly the same thing again and again. There's no reason to memorize that. But you should definitely understand the concepts, right? You should understand that if I want to respond to mouse clicks in this panel, I'm going to have to set up some kind of event handler. And something is going to say, hey, when a mouse click occurs, run some code. So you could see a question where I give you, a chunk of code like what Window Builder would create with a comment saying, add your mouse handling code here, and then you might have to show me what code you would put in that spot to do something, respond to a mouse click, draw a line, stuff like that. And so this other theme that comes out through PA4 and PA5 is this idea of setting things up to happen later on. So we don't make a while loop that says, while mouse button is not pressed, wait a little while and check again, right? That would be inefficient. We register a listener and say, hey, if you notice a mouse click, call this code. So we set things up so that actions take place later on. And the same thing happens when we try to do painting. When you click on your PA4 board and you want to draw a line between these 2 points on the panel, you don't call draw line, right? You can't, because you're not allowed to draw in the middle of your mouse handling code. So what you do is you set a Boolean. And that Boolean says, hey, when you get around to painting this panel, put a line right here. And so you set a Boolean, or you record the XY coordinates in a list or something, right? And then you call repaint. and repaint says, hey, paint needs to be called. And it doesn't call it right then, but it says, hey, we need to call paint sometime soon. And then eventually something will call paint, and paint might have a loop that goes through all your booleans, and when it sees this boolean, then it will say draw a line between here and here. So event-driven code ties in with this idea of sort of doing things, you know, later, and making those things data-driven, right? So we set stuff up, and then something happens. So event handlers, we use this for responding to mouse events. We used it for responding to button clicks. We may have played with something where we resized a window and had some code run in response to that. There's all kinds of events. With Android, we played around with, you know, a GPS location update event. But it's the same basic structure, right? Let me know when something happens by calling this piece of code. And then we just go away, we go to sleep. And if this event occurs, suddenly this code is executing. And so things have to be set up so that if this code starts to run, it's doing the right thing. And this should all be good flashback to Engineering 270 when we dealt with interrupts, if you've done that class. Alright, threads. We talked about making and using threads in Java. And the whole idea is, number one, we extend the thread class. Number two, in our extended class, we make a method called run. And run is like the main program of what we want our thread to do. And then when someone else wants to create the thread and have it start executing, we call that thread's start method, not run. We call start, and start does two things. It creates a new thread. It starts a separate process executing, and then it calls run. So it executes the main program, basically, of this new thread. And that's really all we do every time that we've made a thread in Java. Extend the class, put your main code in a run method, and then someone else constructs your class, calls the start method. Alright, and passing this to a constructor, sharing information among threads, let's break that down a little bit. This came up in PA5. And so, for example, man, I feel like doing this in the editor because I haven't written code in lecture in a while, but we'll do it on paper. So let's suppose we have some main class running. So here's class whatever, and here's, you know, some method. And we're gonna extend the thread class. We're gonna have a class myThread, which extends thread. And somewhere down here is a public void run. So this is what gets executed when you call start. So in our class that's going to use this thread, we might say something like, you know, empty thread equals new empty, and then we might say t.start. Alright, this starts a new thread executing, and then it calls this run method, and it does whatever's inside here in a separate thread. And this method will just continue, you know, doing whatever the next statement is and so on. So that's like the fork in C. That's where this new process begins. So one thing that might happen is, for example, in class whatever, I might have, you know, I don't know, a linked list of integers called index. doesn't matter what it is. I've got some object up here, right? Which is some kind of data structure. In this case, it's a linked list. It may be that I want this thread to be able to interact with this object, right? And it can't, reach back and call something in here, right? It has no access to class whatever. And I can't pass index to the start method because the signature for start has to be, void with no arguments. And I can't pass it to the run method because the run method has to be public void with no arguments. So here's what I could do. Before I start the thread, I could say, t dot save index. And I could pass this, to just some plain method in this class. And in this class, I might say something like linked list integer. I'll just call it index. And then I'd write a method, public void save index I linked list I, and then I could just say, index equals I. All right, so what happens? I construct a new thread that just makes, an instance of MT called T. I call save index and I pass it this linked list. Save index takes that linked list, saves it in this field called index. And now when I say T start, run starts executing, but I can do stuff with index. And this index here is this linked list here. It's shared data. So I have two threads that can both access, this linked list. So you can share information like that. And this is one place where the this keyword comes in handy. So I might say something like, save parent this. And so in here I could have, an object of type whatever called parent. And then I could make a method called, save parent, which takes an argument of type whatever. And I could say parent equals P. All right, so when I say save parent and I say this as the argument, this is, the whatever class that is currently executing this statement. And when this method gets called save parent, P is going to be equal to what this was over here. It's this object that constructed this thread. And so when I say parent equals P, now this field named parent is a reference to this object. And so I could, do stuff with that parent object. And I can get to the fields and methods inside here that are accessible. So this can always get to the thread because I constructed it. I've got a reference to it, which is T. By passing this to a method here and saving it, now everything in here can access everything in here. So you can set up that two-way access. And this happened, for most people in PA5, where, for example, your netthread class maybe needs to access the mouse click code in your J panel, and maybe it needs to access some text field in your JFrame. And your JFrame needs to access stuff in your netthread and in your J panel. And your J panel may need to access stuff in your JFrame, like the scores and the player names and so on. So this lets you, share information between threads, right? Because Swing is a thread and your main program is a thread. NetThread is a thread. And we talked... Yeah, go ahead.
You could have also implemented a J panel with all your network information and had that have all your network functions and and have it implement runnable and have your thread just keep running and waiting for socket information, and you could have it do the 3 of those things at once.
That's true as long as your JPanel doesn't do things like paint or responding to events.
Really?
Well, you can do that, but you run the danger of your GUI hanging if something goes wrong with the network. Right, so if the other player kicks out and it takes a few seconds for the connection to shut down, your GUI would look like it freezes, maybe.
So, if, not to get too far into the PA5 rabbit hole,
that's okay.
Basically, if I had a thread on the network manager just waiting for input from the socket, I was still able, I didn't architect it this way, but this is something I wanted to do later on. But if I called a sync name method or a sync input method or a sync game board size method, I was able to call those from the main thread and have it be separate from the socket lister. So
okay.
Would that still be an issue?
That might take care of it.
Okay.
Yeah.
I was going to ask if you know how repaint is really maybe working under the hood, because I don't know how you would call a subclass method from a superclass.
Well, so when I call repaint, I think I lost my page. So the short answer is no. I don't know how it actually works. I just assumed it was magic. But when I've got my JPanel, so my panel P, and then I say p.repaint. Repaint can just be written inside a JPanel as a method that calls paint. Right, this wouldn't, there'd be no point to this, but it could just be written as a method that calls paint, or a method that calls, paint requested with an argument of this, and it could call that inside what object? I don't know. Maybe another method in the MyPanel class. I guess the part I don't know is how this gets kind of outside of this class itself and into whatever sort of the larger entity is that's monitoring events and controlling when things are dispatched and so on and so forth. I don't know what that linkage is. But hey, source code, right? We could pull it down and find out.
I would almost have to wonder if it's just a method calling paint on the superclass, so it has repaint and paint on the superclass, and it's just a fancier way to call paint, I guess, maybe.
I'm pretty sure it's not, because I think there's a timing issue here. I think if you called repaint 1,000 times and you put a counter inside paint, that counter would not increment by 1,000. But that would be a pretty easy test to run. And see how many calls to repaint correspond to a single call to paint, and I think you'll find that paints only happen once in a while, even if repaint gets called a bunch. And you might even be able to throw some timestamps in there and see if there's a frequency, if it's happening 90 times per second based on refresh rate or something like that, or some multiple of 90 times per second.
Maybe it's filling up a buffer before it does anything.
Yeah. But like I say, I just assume it's magic. I like to picture unicorns like running around and painting with their tails and stuff. All right. So we can share information, and sharing information among threads gets us into this question of synchronization and issues with shared access to data. So we did an example with an ATM. We did a coded example with a voting machine system. But the principle is basically if you have, say, a linked list like this, and you have two threads. You have thread 1, which is trying to delete node 30, and you have thread 2, which is trying to add a node with a value of 35. And both of these have access to the same list, and they're running at the same time. Here's what can happen. So suppose the person who wrote these methods took 222. So they set up, a previous equal to, 10, and that's not what we want. So, or previous next, and here's previous next. And when they get here, they discover, hey, the node I'm sitting on is 30. That's the one that should be deleted. So I'm going to take node 20 and have that point to node 40. Right? So at that moment, thread 2 has done the following. They had, a previous next, and then they moved to a previous next, and they moved to a previous next. And here, they found the first node bigger than 35. So they're about to say, 30 next equals 35, and 35 next equals 40. And this node is about to say 20 next equals 40. Well, so now at this point, what happens, 30 is changed to point to a new node 35. 35 is changed to point to a new node 40. And now this statement executes and says 20 should be changed to point to 40. Both processes finish. What's the effect on our linked list? Node 10 points to 20, points to 40. 35 is missing. And this is the same thing as, somebody deposited into your account at the same time someone withdrew, and the withdrawal got credited and the deposit didn't. And you end up losing money. Exactly the same situation here. And the issue is that this operation of deleting should be made atomic. It should be uninterruptible. And this operation of adding should be a single atomic uninterruptible operation. And if we allow this to get interrupted and we do some manipulation on the list for adding, while we're working on a deletion, these things can conflict with one another. So this would be an example of where the delete method would want to be synchronized. So we'd have some flag and we'd say, hey, once you start the delete method, nobody else can touch the list. And we do the same thing with the add method, and now if we start deleting and someone tries to add, this method will block. And it won't proceed with all of these steps until the delete method is done. So this would change the list to, what we'd expect, 10 to 20 to 40. Release the lock, and then this would start executing. It would come down. Here's previous, here's next. We'll make a 35, 20 points to that, 40 points from 35, and everything works great. So there's a synchronized keyword we can use in Java for this. And the general thing we talked about was this idea of read, modify, write. So we're reading our list, we're making some changes, and we're writing them back into the list. And this read, modify, write sometimes needs to be atomic to avoid potential data corruption. So that was synchronization. Deadlock, live lock are other things that can go wrong when we have multiple processes or threads running. And so the Dining Philosophers was an exercise to explore some of these scenarios. So deadlock typically happens when you have competition for resources and neither process can advance because they need a resource that some other process has. And so I've got a pencil and somebody else has a pencil sharpener, and I'm not going to do anything more until I sharpen my pencil, and they're not going to do anything more until they sharpen their pencil, and they need, all right, have a good one. Cool. All right, yeah, it's been a fun ride, I hope. Yeah, I will see you on Thursday. So I've got a pencil, I need an eraser or a sharpener. Somebody else has a sharpener, they need a pencil, right? They're not going to give up the sharpener until they've sharpened the pencil. Well, I've got the pencil, and I'm not going to give it up until I write something down. I can't do that until I sharpen it. So we're deadlocked, right? And neither of us is going to give up our resources, and because of that, neither of us is going to get the resource that we're missing and be able to continue with our algorithm. And so deadlock, presents as you've got a bunch of processes running, and all of a sudden some processes are just frozen, and it could be a resource contention issue. Live lock is similar, but maybe I'm waiting for a resource and I don't have access to it, so I put my pencil down and I come back in a few minutes and I try again. And maybe I come back in a few minutes and try again, and the other person still has the sharpener and we're still deadlocked. So live lock, you're changing state, but you're still not able to make progress. All right, and then the last thing we talked about was networking. So we talked about sockets as a way of communicating between 2 points on potentially different machines. And this was built on the client-server model. So a server is usually, a process or something that is waiting for connections to be made. And a client is the thing that makes connections to a server. And once that connection is established, who knows what's going to happen. It depends on what the client and server are doing. But a print server, a login server through SSH, a web page server, these are all common examples. And a net.dot server, right, that hangs out and waits and listens to a port, and you can come in and make a connection and play dots. So in Java, there's 2 types of sockets, a plain old socket and a server socket. A server socket is, guess what, it's a socket for a server, and a plain old socket is a server socket for a client. And so server sockets, you don't specify an address because they're on, the machine that you're running, but you specify a port number. So that's the identity of the server socket that somebody else can use to connect to it. And you typically call an accept method after you've constructed the server socket and say, I'm ready to receive a connection from someone. And when accept returns, it gives you a socket that's connected to the client that made the connection to you. On the client side, you construct a socket, and in that constructor, typically you specify the IP address of the server and the port number. And so that gets you to a unique server socket somewhere in the human universe. And if there's an accept method listening on that port, it will, respond to that connection request, and now you have a client socket and a server socket connected to each other. And once you have that, you can use, print writers and scanners, among other things, to do output and input to and from a socket. And when you write into one socket, the other side can read what you wrote, and vice versa. Lots of try-catch opportunities in here because we don't know which of these are going to succeed or fail. If we try to make a server socket on port 1234, but you've already got a netgame running, your server socket constructor will fail. It'll fail with the exception address already in use. And so we use lots of try-catches in here. We talked about the URL class. I'm not going to test you on that. I'm not going to test you on editor panes or scroll panes. Those were done for fun and, examples of where all this stuff can take us. But I'm not going to ask you to write code for that. I think that's a pretty good synopsis of what we've been doing. Any questions on any of that?
Seems pretty straightforward.
Hopefully, so I'm not planning on trying to trip people up on the exam, right? My goal is to just basically, give you a chance to show off your understanding of the things we've been doing. And call it good at that. I got weird stuff going on. So I'm scheduling the exam to be an hour and 50 minutes. I'll be shooting for, I don't know, maybe an hour and 30 with some extra wiggle room in there. But, you know, it's always tricky timing things out. What else can I tell you? I posted an announcement, so make sure that you are logged into Zoom during the exam. Occasionally, you know, ask a question that's like impossible, and or you know, I have a typo that makes no sense and completely changes the question. And so if you're in Zoom, I'll just announce that, and you'll be able to go from there. All right. Well, that's all I got. I'm happy to let you out. You know, 15 minutes early for the last class. If anybody wants to ask about anything or go over anything, or you know, do the last 15-20 minutes here as office hours or whatever, I can stick around until 3:10 as usual. But other than that, you're free to go. I have office hours tomorrow morning. I don't have office hours next week. So Friday morning would be your last chance to catch me in the regular Zoom setup. I'll be somewhat emailable next week, but you know, I've got 2 exams Monday and I'll be grading those and so on. Hope everybody has a good weekend. Thank you everybody for all of your effort and work during this course and during the whole sequence. And yeah, some of you I've had in class for 2 years. Some of you I think go back to CSE 101, so it's definitely been a long ride. But I've enjoyed working with all of you, and I think you've been a great bunch of students, and I think you're in good shape for moving on to whatever comes next in your journey. So I just wanted to thank you for everything you've put into this, and hope you all have a great weekend. And I will see you Thursday for the exam. All right. Thank you.
Thank you. Yeah, thanks for everything, Nick.
Yeah,
Thank you.
you're very welcome.